interactions and the development of constant pH simulation methods. But before we could go through these methods, there is a kind of, let's say, of basic background that all the theoreticians probably need so they can get a little bit quicker to their main point before before they need to be repeating things that eventually can be new to people. So the idea of this initial class, that's why I'm calling part 0, is just to give some kind of a general introduction. But moreover, I think it's nice that you can hear things from different perspectives. Because especially when you look at your keywords, if you remember this morning during the presentation, what's the definition of biological physics? This is something that now is under debate for us, right? And I think I could easily see that everybody can have different opinions about what's computational physics, what is computational biophysics, computational biochemistry, molecular modeling, and we can go on with a different vocabulary. And for different people, they have different meanings. Sometimes it's just a small difference, sometimes it's a bigger difference. I'll try to provide this introduction, a kind of, let's say, of my personal view of this subject. And especially how these two things at the end, they end up more or less in the same place, despite the name that you use. At the very beginning, before I really go through it, we start saying a few words also about what we do in my labs, because a kind of introduction, so you start to get to know us a little bit better as well. We know more about you than you probably know about us, so it's good that we start also to put the game in a more fair situation. For me, when you say that, well, I'm trying to go from computational physics or biophysics to structural bioinformatics, actually, I could change the name, as you can see here, by different options. But for instance, I can take computational physics applied to biological science or biological problems. That can be an alternative name to describe exactly the same thing. And honestly, I think this is easily, probably I'm not going to offend anybody if I tell that this is a cross point where you have the combination of physics, biological science in general. I could also put pharmaceutical science, medical science nowadays, with computer science, where they all meet together. Often, being a physicist, I prefer to put this using the water phase diagram. And this is the triple point. And eventually, if you were not happy, you can do like this, no problem. I'm not going to get offended. But I also add a little bit of statistics here, because especially nowadays, when you have all this machine learning approach, I think we should put this in account. So for me, this is a place where you're going to combine in different proportions these subjects. That's, let's say, the basic introduction. So describe from where I come from and what we do in my lab. I'm not from this place. We are also guests here, as you. Here is São Paulo. I'm coming a little bit from the countryside in a place called Ribeirão Preto. It looks like more a farm. This is the main entrance of the university. And actually, I'm based in a school of pharmaceutical science, where we used to have a department that was physics and chemistry. Now they have changed to biomolecular science. That's the new name of the department. But what we do in our lab essentially is multi-scale and multi-approach modeling. In short, we apply what we more often learn in a physics degree course, how to take a very complex system and make a simplified model of it. This is what we usually call how to make the spherical Call approximation. That's essentially what we do. But of course, we try to do models that we can solve in the computer. And I already introduced to you a few things. I said we do models and then we solve in the computer. I'm already splitting the two things, because very often we put everything together. And for me, there's a clear separation between what is to propose a model, what is really the modeling part, and then once you have the model, how you're going to solve this model. And when you solve the model, you can invoke statistical mechanics treatments in, let's say, a more analytical way, or you can do what we can call computer simulations. But there should be a difference. Another thing that we are really focused, and actually when people ask what I'm doing, or if I'm a physicist, a chemist, or whatever they ask me, my phrase is typically to say that, well, I work with biomolecular interactions. That's how I define myself. I don't think I can put, I can put different hats, of course, but I think this is better. And for me, essentially, a key question is really to look at fundamental interactions, especially electrostatic interactions. Doesn't matter if it's a metal particle, like calcium binding proteins can be one typical problem, We can work with nanoparticles, polyelectrolyte, protein-protein interactions. Even nowadays, we are doing a little bit of protein-RNA interactions. But it doesn't matter the application, doesn't matter the shape, it doesn't matter the difference between the systems. At the end, we all have the same physics. And if you learn the physics, we are able to control and design very specific applications. So this also goes a little bit closer to innovation, to different bio applications that you can just imagine, from biomaterials to virus. You probably have seen that we have a poster from our lab that's dealing with Zika virus, for instance, that essentially is an application of this kind of techniques to a more pragmatic and important problem to this country. Things that we learn here, since we needed to do simulations often for this kind of problems, we try to go in a more, let's say, computational approach that people can say that's bioinformatics. So usually what we learn here, we try to build up servers and these kind of things to try to make this knowledge easily available to people that are not expert in this field. So this is a very brief introduction from what we do in our lab. I can also say something that's related with me, but is also related in general with what we do in computational physics or modeling and simulation together. So a typical case is we take a very complex problem, like this is a microencapsulation. My colleagues at the School of Pharmaceutical Science, they have this problem very often. They have like chemicals that are very sensitive and fragile, so they have to put in a kind of capsid, and they have to deliver this under very specific conditions. So typically they use this microencapsulation process. Of course, this is a complex system, and applying the call trick, we're trying to identify what's more relevant to control this problem. And if you have a kind of, say, of layer that's made up of a protein and polyelectrolyte interaction, we can build up models that we know that they're going to be sensitive in this case, especially to pH and salt. And using these models, we can predict the interesting properties that might be relevant to the experimentalists and even to design under which condition that this can be better used for their application. If you remember in the previous class from Chuck, he was mentioning to you that one important thing could be, a challenge actually, is to predict the protein-protein or actually protein crystallization, which happens to be a protein-protein case. So if we're learning more under which conditions we can have a given protein that they don't know the structure, what can be the cocktail that actually is written here that can be better for them to start their trial, they are going to save money and eventually they can succeed better and have better crystals. So, of course, we are not there yet. I don't mean just our lab, but in general, we have advanced a little bit. But it's already possible to predict a little bit, at least, of second virial coefficients. And this can also something they can measure with light scattering experiments. So probably combining these things on the future, proteins that are very hard to be crystallized nowadays, eventually they can become, we can find alternatives to it, or at least find the best conditions to get some better resolution and so on. I mean, just to try to also to make a connection between what you just heard this morning and what you can see in these slides. Of course, to get virial coefficients in the computer, we use lots of statistical mechanics. For instance, we use what we call potential of mean force that I will describe a little bit later during the next slides. But this is, let's say, a general layout for most of the theoretical approximations, or approaches, I could say. Well, this is a course, right? So if you were new in the field or would like to get some suggestions about textbooks, I'm writing here the books that usually are very useful for you to start. I can see people taking pictures. Don't worry, you have all the slides available to you. So you don't need to be worrying. Of course, you can take the picture, there's no problem. It's also recording, no worries. But I'm saying, like, don't worry if I'm passing too fast my slides, because all the slides are going to be available to you. You have on the home page from ICTP here, okay? I mean, you are welcome to take pictures. Don't get me wrong, I'm not trying to interrupt your action, but it's just to let you know that sometimes it can be quicker, and don't worry because you have all the material available. I'm writing here specific scientific papers, and during the presentation, you are going to see that I'm also going to make citations to other papers and other books. So this is the list more, as I said, more related to the computational physics approach. It's more related to the techniques itself, the algorithms, and you also have classical books for the more applied view of this field that you can see here, especially in this nice book from Philip, the structural bioinformatics. So if you were looking for Bibles in this subject, this can be one more on the structural bioinformatics side. If you already work in the field, I have 2 recommendations for you where you can have more detailed and more recent views of these approaches and these techniques and problems that they are trying to work or trying to solve in the best way. Okay, I already have covered a little bit the presentation, the bibliography, and now we have a few points that I would like to go through. So this is the plan for this part 0. Somewhere here I should break. And this is what's going to be the 3 next topics that I'm going to discuss with you. So as I said, part 1, 2, and 3 is going to be a continuation where I'm going to use this preliminary background for you, to develop the next. Well, this is a nice cartoon. I mean, we are talking about biological things. And you know that life is really a very complex system. I mean, we can discuss details from different sides, from different perspectives, but we all know that this is a very complex. And everybody can say something like this, well, maybe you can describe a little bit better these things. I mean, this was a slide that I got some time ago from a colleague. I don't know where it's the source. If you know, let me know. But I think it's very nice for this situation. I mean, we're all here because we have interest in these kind of problems. I mean, we like, maybe there is something here that you were more focused or have a particular interest, but in general, would you like to study a very complex system? And what can we do, I mean, if you know that this is really tricky? I already told you that we learned something in the physics course that help us. We know how to simplify problems. Actually, this is the art side of physics. You look at your complex thing, you try to identify what are the key elements, and you try to make a model that is able to let you explain what you're observing. And answering a few questions, and hopefully you were able to use this for some interesting predictions. That's essentially what we learn how to do. So if you look at your toolbox, this is what I just mentioned, another title of book that can be useful to you. And there, in this set of tools that we have available, we also know something from statistical mechanics. I mean, this is free energy. Like I can have what we can call the partition function here. I have the inner energy. We have a temperature. We have entropy. So this is the function that, in some sense, can help us to connect the 2 words, the microscope and the macroscopic world. We also know that one important question in biological science is to predict events. Would you like, for instance, to predict if a cell division is going to happen? That's why I have this joke as or this cartoon here. And to predict events, we can ask to anybody in physics that, well, probably the easiest way to predict things is to assume that energy is going to be minimized. And when you're trying to predict general events, we can say that the free energy is the one that should be minimized. So we can make this kind of diagrams here, and you know that, for instance, for a protein to folding, he was supposed to be a protein folding. We know that we have to go to some kind of minimum. And what we need if we like to study such things is to be able to find such a tool to give this prediction. That's, let's say, in a very simplified way, what we need to do. To find a tool that lets us to predict events, predict especially thermodynamics events, like could it be, as I just mentioned, protein-protein interactions. So one tool that we have, a kind of, let's say, easily or more convenient way to quantify these things might be based what we call the radio distribution function. This is an example, radio distribution function of a function here of the separation distance. One, let's say, simplified way to see this is like the probability to find another particle as a given distance from a central particle. So if I'm sitting here in the central particle, what's the probability to find the neighbors? And then you can see that we have all these layers, some empty space and place where higher probability in some way compared to the ideal guy's behavior. Of course, this is not normalized. It's just a simplified way to explain. But it's related for sure with interactions. If you know the pattern of your radio distribution function, you can start getting a feeling if you have very strong attractive force, if you have a repulsive force, what kind of a force you have between your particles. And we can also predict what's the, let's say, the more likely probability for them to be apart from each other. So if I would like to predict if 2 proteins are going to form a complex, I have I need to find some kind of high peak to tell me that there is a high probability for them to be together at closer separation distance. If I have something high that's very far away, I know that they're not going to be like to form a complex. So this is the function that I mentioned at the beginning, and it can be worked out to give you the virial coefficient, for instance. In terms of practical means, the easiest way to do it could be to count kind of histograms. So you divide this as layers, and you count the number of observations that you have between different layers. So here's the volume, here's the number of observations, the density that you have of the whole system. So between, for each layer, you're going to have a value, and eventually you are lucky to have a smooth plot like this. At the very beginning, so telling you a little bit of the history of the things, you can see that people were doing experiments throwing up particles and measuring this in a table with a ruler and counting probability like this. So it was very time consuming. I'm going to show you a slide about this. But just back to what I mentioned about intermolecular interactions and the radio distribution function, we can compare, for instance, different solvents. So here we have tetrachloride carbon, chloride. We have here an apolar solvent. We have DMSO that's like an attractive solvent. And here is one that probably everybody knows, water. That's also can make a very strong hydrogen bond. So we increase the intermolecular interactions in this direction. And as you can see, the peak starts to be a little bit more sharper and higher when we go from something that's apolar to something that can make hydrogen bonds. So this is an example how I can use the radio distribution function to tell me something about the structure of the liquid, the structure of my system. Back to protein-protein interactions, we can measure such things as a radio distribution function at different physical-chemical conditions, and we can compare it with experiments, but we can also change the physical-chemical systems. Like you can change pH, for instance, and you can see that as a function of pH, you are going to have a complex or not. Actually, in this plot, what I'm taking is the logarithm of the function in kT units. This is what we call the potential of mean force, or shortly we can say free energy. So I know that for any value here is smaller than 0, we can say that in terms of thermodynamics, I have a complexation. So I'm able to predict that under these pH conditions, we can have a complex. And in the dashed plot that you can see, the number is higher than 0. So under this condition, they're not going to attract each other. It's a repulsive regime. So practical examples that we can do with this function. That's going to be used for me in the next 3 topics a lot. Using the mean value here, you can also make plots like when is the maximum interactions for different pHs. As you can see, just take the minimum here, and you can plot in a different way. So it's very instructive to know these properties. But how do I generate this? You already know that, of course, by computer is the easiest way, but I mentioned about history. And to get really you back into the business, I don't need to go too far. In 36, this is how people were doing it, pouring steel spheres onto a flat surface and measuring each time the distance between. This is how people, something like this, they were counting the position of the particles, and they were making plots of radio distribution functions and free energy to describe and to understand more the liquid structure, to describe better how was the intermolecular interactions, and even how we know that water is a tetrahedral, has this geometry. So, of course, it's much easier to do this in a computer experiment, right? It took some years for people to be able to do it. You can see that there were papers. This is 36, but they are also mentioned in this paper another study that was a little bit earlier. And actually, in this paper, they are trying to do in 3 dimensions. They have done before in 2 dimensions. So it took a couple of years, something like 25 years, for people to start doing this in the computer simulations. So for most of the people, this is somehow when it was born in the computational physics using the molecular structures. The first structure that people were trying was hard objects, or Lennard-Jones objects. And these are the classical papers where you can see Lennard-Jones particles here, where you also have the integration algorithm that nowadays are very popular in most of the packets that you can download simply from internet to do your computer experiments. So just to let you know how the things have evolved, you can see that in this paper from 67, they were working with less than 1,000 Lennard-Jones particle. And this was amazing for that time. Well, talking about proteins, you heard this morning lots of things about proteins. And if we look into the first simulation of the protein, they were done in vacuum for picoseconds. And they were working for a small protein, BPTI, that has about 70-something amino acids, less than 100. And it was amazing. I mean, people got papers in Nature, and there were publications and more publications, just increasing the observation time and eventually change the force field. This is a kind of a review just to show you from where we left and where we are more or less today. I mean, of course, you're going to see this through the lectures, but you already have a feeling that we are orders of magnitudes, both in terms of the size of the system. We work usually with water, electrolyte solutions, and so on, and you have much larger objects. But this was the beginning of the thing. And actually, for some people, this was already the beginning of what we can call structural bioinformatics. That's why people say that if you look at your bioinformatics, this is one of the first, let's say, subdivisions of bioinformatics. Well, the idea of a radio distribution function, or this idea of potential of mean force, this kind of probabilistic view, you can see traces of it in different names that people use for potentials that you can extract from observable experimentation, like protein data bank or this kind of data. So these are just more examples about models that were built up using experimental observation. So after after this brief introduction about this computational aspect and this kind of practical tool that we can use to analyze results, let's try to create a definition about how we can define structural bioinformatics. There are collections of papers. There are lots of things people are trying to come up with a name. So as I said, it's the same for biological physics. You can read different things. But my favorite quote comes from this paper here for Mark Gernstein. What is bioinformatics? According to his definition, I mean, this is from his paper, it's somehow that you make a conceptual view of biological science in terms of molecules, especially using physical chemistry ideas, and apply informatic techniques that are derived, of course, from math, computer science, and statistics to understand and organize information associated with these molecules. And then I'm bolding here on a large scale. Because people, in some sense, they were doing something similar, but in a small scale, where they were taking one protein system, they were studying, for instance, in vacuum, like they did in '97. So if I stop here, this could be easily the definition of structural bioinformatics. So probably, if I repeat that experiment, make lots of mutations, and try different environments, that could fit in this definition. But if I just study very carefully one small system or one particular system in one given or two given conditions, I'm not on a large scale. So probably it's better to use the computational physics or computational whatever you want than structural bioinformatics. So for me, the key definition for structural bioinformatics, or the key difference between the bioinformatics and the biophysics approach, is that you put on the large scale. That's the point. So if I try to organize things that can be done or classify typical problems here, we can go from the omics side that's more related to database, to the statistical side, alignment of a protein structure, alignment of whatever you want to do, data mining, these kind of things. We can have something that starts to go a little bit closer to physics or using physical ideas. And then we can put here the molecular modeling, especially if you have something intermediate that you have partial information from how should be the physical interactions, plus some statistical analysis. And eventually you can go to this side where you usually were using more really physics-based model, that you put the physical information. Could be ab initio, could be some effective model that you are just using some force field to do the things. But I think this is a way to try to organize all the different problems that we can deal or we can study in the structural side. Let me take one particular problem that was also a question this morning, protein structure prediction. So if I have the sequence and I would like to predict how is the 3D model, well, from a practical point of view, if you're not really interested in the driving force and the mechanism part, I can go to Google and essentially give it a sequence. And if Google has a person behind it that could guess how is the 3D structure, that's fair enough. I got the 3D model. That's one way. Typically, we can let's say, split into different approaches. We have much more the biological approach that we're going to use something like a database to try to find a protein that has some kind of similarity. You go for like using model. That's a very common tool to try to predict, especially loops that are missing, flexible parts on the protein structure, or if you have a model that you know that just a few mutations are different, it can be really, and you have, of course, for one of the proteins, you have the solved structure. This can be a nice tool, but behind it, I can essentially use the statistics, I can use the person, doesn't matter. As soon as I'm able to provide you a 3D model that you can do whatever you need to do if you are with this information, it's okay. But typically, from the physical side, would you like to study the mechanism? Would you like to understand what are the driving force? Would you like to predict this in different conditions? I mean, not just in the same pH or the same salt air you have in the crystal data. Would you like to do the predictions in other situations? So in this case, we need to invoke the physical approach. And here, we started with a problem. We have to choose or to make a model. And then the second step is to simulate. And when I say, I mean, this is division between modeling and solving the model, of course, one critical step is the force field. Depending on your application, depending on what system you'd like to study, depending on what you are after, you might have to make a choice. Typically, we have a compromise between accuracy and simplification, a reduction in number of interaction sites, what's really a practical relevance of what your question is. And it's really the balance between such things that's going to describe what ingredients you are going to put in your force field. How is going to be your zoom. If you're going to look into the electronic structure or in a very, very coarse level description. There are posters here. I didn't have time. I just heard that they are studying very large objects. So we have to see what level of resolution they are using to solve such problem. And also, what kind of computer power you have available to solve such problem. That's another thing that enters the game. But once we have defined what's your answer and what kind of accuracy, what computational resource you have available, these kind of things, then we have to think about what's going to be the best technique to solve this problem. I'm listing a few techniques that probably you have heard about before. I'm going to make some very small comments about MED and MC. Poisson-Boltzmann is going to be the topic of Eduardo next morning. So tomorrow morning, you have more details about Poisson-Boltzmann. Genetic algorithm, I don't think we're going to cover, but probably you can find in the books that I said, or you can make any questions later. But I'll just make a little bit, cover a little bit these two topics. So for any system, we can start like this. I have the real world, I have the problem that I want to solve, and I need to make a model. And then, of course, when I make a model, I have to decide if I'm going to use a theoretical approach or a simulation approach to solve the model. Very often, when I go to the theoretical side, I need to invoke additional approximations. So I have to introduce new simplification in my model. Here, you get the results from the simulation. You have the theoretical data. You can compare both, also to test if you do exactly what your model is supposed to do, how should be your results. And if they are in agreement with the approximation that you have invoked, you can do a comparison between the experimental data and vice versa. I mean, you can do all this triangle here. What I would like, first of all, to stress, this is a kind of a picture that's very often shown under these conditions, is that the three things, they work together. There is not something that's better than the other. I mean, we need each other to do a good job. So very often, you learn a lot from the experimental side to be able to develop good models. And we hope that we can contribute with them eventually to provide some information that can be used to speed up their time and to save chemicals. So this kind of general approach is what you probably are going to see in most of the theoretical studies, even if they are not clear like I'm trying to show here. But in terms of the simulation, then we go through the same techniques that I just mentioned in the previous slides. So just to try to give an overview of what I just said, I try to put here that your choice for the modeling, for the sampling of your system, is going to rely in the choice that you make for all these 3 points here. So what's the property or quantity, and actually what's the question that you were after, how is the accuracy that you need for your system, and especially how much available power you have. So very often we have to invoke simplifications because we are lacking computational resource and would like to give a contribution as quicker as possible. Sometimes you have large computational power, but you need to repeat your calculation so many times that you need again to reduce a little bit your model. You can remove a few details to try to be able to run all your calculation for all these conditions that you need. So it's all the time this compromise that you have to keep in mind when you're doing modeling. To try to exemplify these in practical questions, I just took you one system here, column modeling, and one peptide that's represented here as a binding complex. So what kind of questions that usually we are trying to answer? So there are general questions. It doesn't matter exactly what system I have. They can be very general. Like, as I said, for instance, it's something that's driving my work. What are the fundamental interactions? What are the contribution of individual amino acids? What molecular mechanisms are involved in this complexation? What's the contribution from the environment? But I can also start to make more specific questions. How is this complex? In what condition it's formed? Is it stable? What kind of context I have? For instance, it's using the contact residues that we develop a method to predict epitopes in viral proteins. So this can be something useful, as I said, for practical things. What's the mean conformation of the peptide? What's the mean conformation of the protein? How this is affected by the environment? Where we have the sites that have most changes, they are pKa's. They're chemical constants. Where they're located. I mean, what's the effect if I have the calcium bind in this protein? It's going to change the conformation. It's going to be easily to bind to the peptide, or it's going to unfold the protein and release the peptide. So mutations that can be critical for all this process or for other process. These are typical examples that we try to address when we do this computational approach in structural bioinformatics using computer simulations, typically. So I mentioned models, and I didn't describe all the kinds of models. Just was very briefly to say that you can go to the quantum level or you can go to a more coarse grain level. I'm trying to make a picture here about my different spherical calls or different ways to represent my call. You have, of course, the biological approach that you can put all the details. Then you can start to have some kind of more chemical approach that you try to get rid of a few details, and then we go to physics. Eventually, your protein end up like a big, hard, or a big Lennard-Jones spherical object with a central charge. You can be surprised at how many predictions you can make with such simplified model. A good example is the so-called Thunford-Kirkwood model. That's essentially something like this, a kind of intermediate thing. And especially if you are interested in calcium-binding proteins or metal-binding proteins to describe salt effects, it's great. I mean, you get more precision in this kind of very simplified model than you can get in very detailed atomistic simulations because you were able to sample enough of what you need. So that's another issue. I mean, sometimes we put all the details and we believe that we're going to get a better answer. And unfortunately, this is not true. Sometimes it's the opposite. So another thing to keep in mind. But instead of looking to this representation, we can also take one of the ideas that Friedman has proposed many years ago in one review paper, where he classified your models that in physics we like to call our effective Hamiltonians. And we can look to the quantum level or subatomic level, where the definition of a particle is what we have as nuclei and electrons. We can have something that's intermediate, that is what they call the Born-Oppenheimer level, that the definition of a particle will change for the solute and the solvents. So a cartoon for this would be a system like this, but here in the presence, I also have the explicit water model and ions and contra-ions. I can invoke extra simplification, and I can go to the so-called Macmillan-Meyer level. So here, instead of have all these solvent and solute particles, I only have the solutive particles. So I take the solvent as an average property. I start working in the so-called continuous description. Essentially, I reduce the degrees of freedom. I reduce a lot the CPU time. You have to keep in mind that usually an interaction in your computer, it takes on the order, I mean, the CPU time is going to be on the order of the number of particles or number of points that you have in your system with the square. So if I can decrease by half, you can imagine how much I gain in terms of performance. So this is the trick that usually is done to simplify things. But of course, I can only do this trick if I'm not, depend on the property that I'm interested. If I would like to study hydration process that happen at the interface between the biological molecule and water, I can never go to the continuum level because I'm not going to have a explicit model there. So I have probably to stay here. This is typically what you have in packages like Gromax and all these simulation packs that you heard. As also something that's somehow between these two things, we have classes of a Macroscopic model where we have the description of your solute, your protein, can happen in different levels. You can have what we call the coarse grain description. So this is also something that's intermediate. The general idea, I mean, how we calibrate this model is typically like this. You propose a function. This is an example of an atomistic description where we have the bound part, the angle part, the Lennard-Jones and the charged particle. So you do your simulation. Could be a Monte Carlo, could be a molecular dynamics. You get your results, you compare with experiment, and you see if it's okay or otherwise. You go there and you start to reparameterize your models until you get a given property that's going to be reproducible. There are a list of things. As I said, I'm not going through all the details, but it's good for you to know that very often this data, they come from an experimental source. So you calibrate your model under a given condition. And there is not a guarantee that this is going to work in all conditions. So this is the first warning that I like to stress to people, that when you're using any kind of model, you have to be careful for which conditions that your model have been calibrated. If you take, for instance, a protein, and you have a model that was developed specifically for that protein that works in the conditions, so the models were designed to give the protein in the crystallography conditions, for instance. When you change your parameters, how do you change if you don't know, if you don't have your experimental data? So we have to be really careful for such things, because most of the force fields, they were calibrated using some kind of data that happened in specific physical chemical conditions. So we are specifying temperature, pH, salt, macromolar concentration, and so on. When you apply these in conditions that are far away from this calibration, we hope that should work, but there's no proof of it. Okay? But anyway, you have some list here of properties that I hope you can go through later. So I don't think it's the point to go into the details, but anyway, it's good to know that there are sources. And examples of force field might be more useful. So let me make some comments, about the history of these force fields. Probably the classical paper and the beginning of this atomistic description, we can go to Lifson. By the way, I don't remember who was, but I think in the morning someone make comments about the three guys that got the Nobel Prize, Michel Levy, Ariel Warshel, and I think it was Chuck, right? Yeah, and Karplus. All the three guys, they have been working with Lifson, so they got inspired in this lab. At some moment, they have been there. And it's here that we start. You can see actually in this paper, that's the contribution of Warshel. And this is the beginning where they have a proposal for the first time mathematical functions, not like this, but in this, that they have introduced Lennard-Jones and charges in their models. And it was called consistent force field. This is the birthday, in some sense, of the molecular simulations force fields that we have nowadays. I got this also from a friend, so I don't know the source, but it makes sense to me that you can see in a kind of a historical way how these different force fields, they have evolved, different contributions from different labs, but all them they have in common the Lifeson lab. And it's probably easy to trace, just look into the function that they have published in this paper and what you can have in different force fields and the different versions of the force field. Another remark that I like to do often when I'm teaching this kind of things here about force field is to remind people that for the same name of the force field, you needed to remember that there are different versions of the force field. Here's just 2 examples, but there are many more functions, even for Gromos or for any other force fields. So you have to remember which version you're using, and if the version that you are using is really ideal to the system that you're trying to study. So try, first of all, to take a look in the literature to see if people have been using the same force field, or either for the same system that you were studying or for something similar that you were studying. Because very often you can see that people take the worst force field for that system. They get results, of course. You just run the software, you get numbers, and sometimes you do understand later that, well, that force field was not really suitable for the system that I had. So keep one eye before you start. It's better to spend some time looking into the literature before you go through your simulations. Although they look like in some way similar, they have the same source, the parameterization can be different, and it's often the case. I mentioned about this mesoscope level that we can call coarse graining. And just to exemplify that you can use your imagination to do different courses, I took a slide from Shell, a guy from California, where he showed here a representation in the atom and the different levels of coarse grains that you can have. So sometimes you just start to aggregate, to cluster a few atoms, like try to get rid of the hydrogens, then you can cluster usually using functional groups. But I can also define, instead of using an atomic description, I can have a more mesoscopic description based on the amino acids. And even further, depending on what I'm after, it doesn't matter the details. We can simplify things, and as I said, any square, if I can go and decrease the number of interaction sites, I gain CPU time, so I can cross the barrier of time and scale of my system. Examples of this coarse grain force field that are very popular. One is probably Martini. Probably this one is the most famous one. And you can see that, for instance, for some amino acids, they were able to use just 1 bit, like alanine is one example, but for arginine, they try to use a little bit more of the structure. They try to use a little bit more of the functional physical-chemical approach. So just one example. And if you are Latin American, we are all proud to have the CETA force field in Uruguay. So it's another kind of force field that has different principles. Because this one was more, how should I say, they had the target to be able to reproduce structural properties. So if you were aiming to study more structural properties, in principle, this one is more suitable. And here is, I would say, it's better if you were trying to work with more, let's say, general thermodynamic things. Just to try a few, let's say, tips about these things. But this is not just, so simple. You probably have to take a little bit more care before you use such things. For instance, based on a few tests that we have done for electrostatic interactions, this model screens too much the interactions. So if you were trying to study electrostatic driven process, you can end up into troubles using Martini. CETA seems to respond well in some situations. In other situations, we also have trouble. So but anyway, this is just an example. Okay, before I forget, there are also things that from a physical perspective can be quite nice, and they are in some way popular, but people somehow, depending on which community you are, they never heard about this. So there is something in protein, especially to study some aspects of a protein fold, that's called the HP model from Ken Deal. This model is just an adaptation what we have as a Flory-Higgins theory, that's a latency model. But they do usually in 3 dimensions. Here's just a representation, in 2 dimensions. Which happens also to be some kind of evolution of another model that we have in colloidal science called the Bragg-Williams theory. Essentially, you mix 2 types of chemicals, you assume that they have the same size, they only have very short interactions, just neighbor interactions, and of course, there is no interaction between the first particle and the last one here, just the first layer, and you define a parameter that's going to give it interaction, and you sample your system. That's a very basic model that's used in colloidal science that has been adapted to study polymers. Florida Higgins theory is about this, and it has been later adapted to study proteins. But they can also provide some information that can be useful for you to understand a little bit better the experimental system that you have. Okay, but I would like to remind that there are such simplified models. And the reason that I mention this is also because I think it's a good case to show mistakes that you should avoid. I mentioned a lot now about electrostatic interactions, which happens to be a long-range interaction. So if I would like to study something that has a long-range interaction, can I use a model that I'm assuming that just the first neighbor is going to give me an answer? I can only do this if I'm working in a very high salt concentration where I'm able to screen out all the electrostatic interactions. Otherwise, this model is never going to work. So these kind of things that we have to keep in mind when you're going to select models. So that's why I think this is also good in a kind of illustrative for the same thing. Okay, I don't know if Eric is going to be able to give you a talk. He's the one that got sick. But he was going to talk to you, or he's going to talk to you, you're going to confirm during the week about inverse approaches, inverse Boltzmann and inverse methods. The idea of an inverse method is a little bit different than what I just showed about the Monte Carlo approach. So anyway, it's good for your knowledge. Usually, you start with the experimental data. You try to have a set of configurations, and you use this set of configurations that are produced to generate your model. So you do in a direct way. So this is a way also to develop models. And the inverse Boltzmann or the inverse Monte Carlo approach is in this direction. Okay, I stop here, and if he continues, it's good. Otherwise, at least you have an idea that there are inverse methods as well. Just two classical examples of such things is the one that was developed by Florian Platt, and the other version that was developed in Sweden, closer to Roth, from Atlaxon and his team. So these are the two approaches that they use in these strategies. You can look at these two papers where they have all the details, and they have been using such methods to really study very, very large systems. So it's something that's appealing. Okay, I make some comments about the modeling part. Let me make a few comments about the solution of the model that can be, as I said, the basis for the next talks. The MED part in a very, let's say, crude way and a simplified way is like this. You take a structure, you use one of these force fields that's going to define how your particles or your sites are going to interact with each other. You calculate velocity positions. You, of course, first you compute first velocity positions, and then you have one point in your trajectory, and you keep this in a loop until, given a criterion, you find the convergence. That's, in short, what we're doing. I mean, essentially, we're applying Newton's law and some numerical algorithm to solve an equation to predict position using the force field that you have to compute your force. That's what we do. If you'd like to practice a little bit, and so we can discuss during the week if you were a beginner in this field, I recommend you to follow this tutorial. There is a link here. You can simply download the Gromex from internet. You can run, and during the breaks, during my working group section, for instance, you can come up so we can discuss. You can do this like in 1 hour in your laptop or using the computer lab here to do the exercise. There are several packets that you can use nowadays for molecular dynamics, for classical molecular dynamics, even more than is written here. I'm just highlighting, let's say, the ones that seems to be the more popular ones. Gromex, I would say that NUMED, Tinker, and LUMPS. Probably these are the ones that are more popular. But some research labs, they also have their own force field or their own packet together for their force field. Like I have one that's called OPEP6, for instance, and it's not available like this. We don't have infrastructure to distribute. It's a partnership with a lab in France, but essentially we are doing the same. And you can write your own code. I mean, just remember that when I started, for instance, we didn't have all this code. We had to write all the codes ourselves. Of course, they were not complete like we have nowadays, but it's something that you can always do. For Monte Carlo, it's a slightly different. I used to compare to people like this. Suppose I'd like to know the probability to find people in this room. I can put a camera, actually I think there is a camera somewhere, recording all the time, and you can film during hours, and we can count the frames, how many people have been here, and we can do the math. Another way could be like from time to time I just come here and take a picture, and then on my way I let it fall down and I mix it up the order, so I lose the order, but I still have the information there. So probably this is a way to see the difference between molecular dynamics and Monte Carlo. But the idea in Monte Carlo is like you have a configuration, you try a trial movement, and using an acceptance criterion like minimize energy and put the entropy here, you define if you're going to accept the new configuration or not. So if you remove this Boltzmann weight, essentially you have a minimization criterion. It's when you put the Boltzmann weight that you start to introduce entropy, and at the end you will minimize the free energy of your system. So this is really important. You generate random numbers, blah, 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 but that's what you're doing. You just produce configurations. And instead of calculating force, you calculate energy, you accept or not, you update an ensemble, and go through. I put here 10 to the power 6, but of course this depends on your system. They are, instead of spending time in this, let's say, more methodological part that's more well-known or is easily found in books, I decided to highlight a few details that usually people forget about Monte Carlo, and I think they are critical. It's really related to the convergence. So if I take a simple system, like just a colloidal-like system, I have here screening the Coulomb potential, a small number of particles that are interacting using these very simplified force fields. Essentially, it's the Coulomb law and a screening factor given by the ionic strength. If you minimize the system very easily, you get your energy to fluctuate around the minimum. So energy, by default, is going to oscillate around the minimum. You have this implicitly, or your force, your algorithm to work like this. But depending on what system you have and what property, you have to be careful. I'm just taking a slightly more complicated system. I'm connecting the beads here by an harmonic spring. So I put two charges connected by spring and I form a model for a polymer, a polyelectrolyte. In this case, I can easily see that the energy is going to repeat this behavior here. It's going to oscillate around the minimum. But look at some specific properties. As you can see here, the end to end. Just measure the distance between this point to this point. And you can see that for the same number of observation time, this property has not converged yet. So very often, what you can see in published papers by well-known people, I don't mean beginners, it's not a young forum, but it's like if you take really professional guys, sometimes they say, well, it has equilibrated, so I use my analysis. And this can be a big mistake, because your property maybe is not properly equilibrated. So keep this in mind before you do your Monte Carlo simulations. Try all the time to check if the property that you are really trying to quantify has already equilibrated, not just energy of your system. So this is one important take-home message. I just would like to add a little bit, because probably you have wondered, at least I know people that all the time they make this question to me. Well, in GROMACS, in most of these packets, people are doing molecular dynamics, so if you were dealing with atomistic force fields. Why it's not often the case that you see Monte Carlo simulations? The answer was given much early, on the 8th. This is a paper from Andrew McCammon, where he can show that if you have anisotropic forces in your system, Monte Carlo is not going to be that efficient. Actually, it can be tricky. They are discussing the efficiency of Metropolis Monte Carlo in this case, and you can see that this can give users trouble, especially under these conditions. So this is the reason that most of the simulation packs that are simply available for you to download, they don't do too much of Monte Carlo. Monte Carlo is going to be very good and very helpful if you have a simplified or coarse-grained description, but it's not going to be good if you have atomic simulation. Especially to work in the continual description, Monte Carlo is going to be better. I would like to finalize trying to organize everything that I said in just one slide, and also trying to show another kind of example that we are driven this field nowadays. It's really applications where you can take a sample from patients It's pretty easy now to use the next generation sequencers to get the whole genome sequence, and from here we can get the proteins, blah, 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 these kind of things. There are lots of course, computational and biophysical and biochemical things here, but using the computational physics, as you can see here, holding the whole thing, oops, you can do the practical things, the pragmatic part of this. That's from rationalized process to design or redesign new applications for the proteins that you get from here. Exactly this is the process that people were doing now to try to understand a little bit more about the coronavirus. They take samples from the patients and they try to understand what antibodies they have there. You can use this to also try to identify new targets that you can use to eventually to find the best antibody to kill the virus or a specific drug that's going to interfere. So this is the way that I see how the computational physics and the structural bioinformatics, they are coupled to each other, or how we can define. I see this as a foundation of this whole thing that can give you also eventually a new drug or a solution for your problem. I'm not alone in this, so I also have support from someone else. I took one title in computational physics that he exactly mentioned the same thing. So he didn't describe in terms of biophysics, but it's the foundation of the computational science. So this is, let's say, my personal view and that I share with this guy. So this is, as I said, it's just an introduction for things that we're going to continue in more specific ways. Of course, I'm welcome to take questions. Otherwise, I'm using the first slide from this morning open section just to make a transition between what I said and we're going to discuss in more details during my next class to what Rolf is going to start talking to you in the next hour. So that's all for my part 0. Questions? If you don't have, we can make 2-3 minutes of a break so Rolf can get ready and we can continue for about 1 hour before we have the coffee break. While I'm here, you can make questions to me at any moment as well, okay? So thank you for the first round.